Welcome to the first discussion in calculus. Every calculus student should be familiar with this notation, f of a. It refers to a value of the function when x is a. So the notation f of a denotes the value of function f when x equals a. Thus, f of a equals m refers to the point a comma m, a being the x, m being the y, which is a point on the graph of the curve y equals f of x. In this discussion, however, we're going to be talking about limits of a function. And limits are not necessarily the value of the function at a, but instead are the value that the function approaches as x approaches a. Let's talk about the notation for a limit. The notation LIM stands for limit. The argument of this limit is f of x, and this underscript is read x approaches a. So this is read the limit of function f as x approaches a, or the limit as x approaches a of f of x. Now the limit, as we said, is some value that the function is approaching as x gets closer to a. So looking at this example, what we're looking for is as we get close to a, as we move along the x-axis moving towards a from the left and from the right, we're looking for the value that the function is headed towards. What value does the function get sufficiently close to as x gets arbitrarily close to a? That value is called the limit. In this example, the function is headed towards L. So the limit of f of x as x goes to a is L. The value of the function at a, however, is this point up here, which is m. So notice that the value of the function at a is different from the limit at a. We can also have limits at infinity. Here's the reciprocal curve, f of x equals 1 over x. For the positive values of x, we have the curve drawn. And we see that as x gets larger, this graph starts to mimic the x-axis, the line y equals 0. We call that asymptotic behavior because it approaches this asymptote. Asymptote is some line that a graph will mimic. So this graph will mimic the horizontal line y equals 0 as we go out to infinity. So the limit then of the function as x goes to infinity is the value that you can get sufficiently close to as x gets arbitrarily close to infinity. And that value here is 0. Now, this function will never equal 0. 0 is not in the range of this function, so it's not a value of the function. However, it is the value that this function approaches as x goes to infinity. And that's the idea behind the limit, some value that a function approaches. Now I want to reiterate that the limit is not the value of the function. The limit of function f as x approaches a does not refer to the value of f when x equals a. Indeed, if the limit of f of x as x approaches a equals the value of f at a, then we have a special condition called continuity. And we'll talk more about continuity in a later discussion. Now let's talk about one-sided limits. Let's look at this function f of x. We see that the value of the function at a, if this is our a value right here, then the value of f of a is 2. But what does the function approach as you approach a from the right? What is the value of the function going towards? Well, it's going towards 2. We call this a right-handed limit, and notice the notation. We use a superscript plus sign to the right of the a value to show that this is the right-handed limit. You would read this, the limit as x approaches a from the right of f of x, and it equals 2. Now the superscript negative indicates the limit of f of x as x approaches a from the left. And notice it's a different value. As we approach a from the left, the function is headed towards 1. When these two values are not the same, the limit does not exist. We write D N E for does not exist, because there isn't one number that the function is approaching as x goes to a. From the right it's approaching 2, but from the left it's approaching 1. So there's not one number that the function is approaching. Therefore, the limit does not exist. That gives us the self-evident theorem. If the limit as x approaches a of a function exists, then the two right-handed limits, the two one-sided limits, the right-handed limit must equal the left-sided limit. So the two one-sided limits will be equal if the limit exists. Here's an example of that. Notice that as we go to a from the right, this function is headed towards the value L. Same thing happens as we go towards a from the left. This function is coming down to L. Thus, the limit of the function as x goes to a is L, because that's what the function is approaching L from both sides. You can get sufficiently close to L as you get arbitrarily close to a. Okay, we've been looking at graphs in order to talk about limits. Let's finish with how would we just evaluate a limit given just the algebraic expression of the function. Here we have the limit of a linear function 2x plus 5 as x approaches 3. We will use direct substitution. Direct substitution is when you substitute this a value here, it's an x value, and you plug it in for x. So we will plug it in, we will substitute it in for x. We have 2 times x plus 5, so plugging in 3, we have 2 times 3 plus 5. That's 2 times 3 is 6 plus 5 is 11. The value of this limit is 11. Now direct substitution only works if the argument is continuous at this value, which we will talk more about continuity later. But frequently it will work if this, under certain conditions when this is continuous, you can just direct substitute. Like in this next example, the limit of the reciprocal function as x goes to 2/3